In the last few videos, we've been looking at hidden Markov models, which are a family of sequence models that have latent variables in them. And at the bottom of this slide, I've just reminded us that an HMM specifies a joint distribution over these latent variables. They're the x's here, and there's one of them for each time step, and the observed variables are called y. In the next set of videos, we're going to look at two different problems. Firstly, how do we estimate the latent variables here given a set of observed y's? So this is sort of something which should be essential if you use these things for speech recognition or removing noise from signals, for example. Y would be the noisy signal, and X might be the denoise signal, or Y might be the speech waveform, and X might be the set of words that gave rise to that speech waveform in the first place. And after we've done that, we're then going to look at a second interesting endeavor, which is to learn these parameters from data. So how do we end up learning the parameters from an observed set of variables y1 to t? Before we dive into the nitty-gritty of inference, though, I wanted to take a step back, because one of the things that really confused me when I came to study HMMs was the huge variety of different ways of performing inference. When we looked at previous latent variable models, like our mixture of Gaussians model, it was very obvious how to approach inference of the class membership of a observed variable. How do we figure out, which Gaussian it came from our mixture of Gaussians? That there was no ambiguity about the inference problem there. But for sequence models like HMMs, that's not the case. There's actually a variety of subtly different inference problems, and there are different algorithms for each one. And I'm going to articulate that through the use of this little diagram at the top here. This diagram has rows and columns. The rows refer to two different types of inference setup. The first one pertains to what's commonly called filtering. And in filtering, you have access to the observed data only up to the current time point t. So this is supposed to mimic a sort of online setting where data are coming in one after the other. So you're seeing more and more of the sequence as the sequence progresses. And at any one time point, you want to estimate latent variables where you've just got access to data y1 through to small t, okay? So this is sort of suitable if you were in a robotics application, say, and you constantly want to estimate the position of the robot as new data are coming in. In the smoothing setting, this is more like a batch setting here. And in this case, we're doing perhaps offline processing of sequences of observed data, y1 through to big T. We get to see the whole sequence now. And maybe we want to estimate latent variables given that entire sequence. So this would be perhaps appropriate in maybe a scientific experiment where you've run the experiment, you've collected the data, and now you want to go back and infer what the latent variables were for the whole sequence. You don't want to do this in an online fashion because you want to be as accurate as possible. And to be as accurate as possible, you need to use all of the data that's available to you. And we're actually seeing an example of this kind of setup at the very end of these sequence modeling lectures when I talk about some extensions. And in that case, people are trying to estimate the position of an animal in a environment. That's the XT, given video camera recordings of that environment. So little movies that they've recorded of the environment, that's y1 to t. And they want to go back and make the best possible estimate for what the location of that animal is in the environment at any time point, given the entire sequence. There's no need to be online in that setting, no need to do filtering. Instead, we'll be doing smoothing. Okay, so this is one axis, one dimension of possible inference algorithms, whether you're doing stuff online and want to do filtering, or whether you are in a smoothing setting and therefore offline or batch. So this is also called offline. There's another axis or dimension of variability here, and that's whether you are interested in estimating marginal distributions. So the marginal distribution over a single variable. let's say xt, or whether you're interested in maintaining dependencies in your inferences and are interested in the joint distribution. So let's take the smoothing case for a concrete example of this. In the smoothing case, we might be interested in estimating the marginal distribution over each variable, xt, given the observed variables y1 to t. Or we might be interested in the full joint distribution, where we're interested in x1 through big T, given y1 to t. And different things have different use cases. For example, if you want to learn the dynamics of the system, you really need to know about temporal dependencies, in which case you need information from the joint distribution here. You need to know how xt co-varies with xt plus 1, say. Okay, so that's the first thing. There are 4 possible distributions that we might want to compute, depending on whether we're interested in filtering or smoothing, or we're interested in the marginal or joint distributions. And so you'll have, in general, 4 different algorithms for computing each one of these quantities. And there'll be different algorithms, it turns out, of course, for linear Gaussian state space models, LG-SSMs, and for discrete hidden state HMMs. So already we're up to 8 different inference problems, depending on which model you want and which in this table, which distribution in this table you want to calculate. Okay, so that would be bad enough, right? That would be complicated enough. But it turns out there's another set of things that people are often interested in, and that is performing point estimates of quantities. Everything up here we talked about was about distributions, but in many cases, people want the best estimate of the latent variable. So, for example, in a tracking problem where maybe you're tracking aeroplanes through the sky from air traffic control based on noisy radar measurements, you might be interested in the probability of xt given y1 to t, which will give you, a distribution over the location of the aircraft at any time point. We might also want to know what the best estimate, the most likely location of that aircraft is for planning. And for that, we would want to compute a point estimate for the location of the aircraft. Now, there are 2 different types of point estimate that we might be interested in. The first one just takes each marginal distribution, like we talked about up here, and finds marginally the most probable x of t. And I'm going to call that xt star here. And the second thing might take, instead of using this marginal distribution, might take the joint distribution, and jointly it might find the most probable sequence. And I'm going to call that x prime 1 to t. And what I want to take a few minutes to consider is why or if these things are different from one another. Is it actually the case that the vector formed by taking all of the xt stars together, so I'll denote that as x star 1 to t, 1 to big T here, are there conditions under which this is equivalent to or equal to the most probable sequence? So is the set of most probable states at time t, marginally most probable states at time t, is that equivalent to the most probable sequence? And I want you to pause the video here for 30 seconds and consider this problem in the case of linear Gaussian state space models. So this is linear Gaussian LG-SSMs. I realize I didn't define that in the previous lecture, so I'm defining that acronym, in words here. I want you to figure out, are these quantities the same for LG-SSMs? And I also want you to think about whether it's the same for discrete hidden state HMMs down here. So pause the video, think on this for 30 seconds, and then restart it again, and we'll talk through the answer. Great. Okay, so here's how I would approach this, and let me make some space so we can work through this above. So first off, let's consider linear Gaussian state space models, the first question here. Now, we know for linear Gaussian state space models, if I write down the probability of x given y1 to t, let's assume that dimensionality of our hidden state here is equal to 1. So the dimensionality of each x is going to be equal to 1, just to make things easier. But what I say will be true in the general case. We know that in that case, we can consider stacking all of the x's on top of each other into one big long vector. And because everything is Gaussian, we know that the posterior distribution is also Gaussian. So remember, this was a model where the latent variables and the observed variables are related by just linear Gaussian transformations. And so the posterior distribution over all of the x's, and now I'm imagining this is a little vector produced by stacking everything on top of each other here. This thing is Gaussian distributed with some mean, let's call that mu1 to t, and some big covariance matrix. So the mean is a t-dimensional vector again, and the covariance matrix here is a big t by t covariance matrix. Maybe I'll just notate that like that. Good, okay, so that's sort of fact number 1. Now, we can now consider marginalizing this to form p of x little t given y1 to big T. And we know from the properties of Gaussians have this really convenient property that the marginal distribution over xt, we can just figure out by going in and picking out the relevant element of the mean mu and the relevant element in the covariance matrix. So this thing also turns out to be a Gaussian in xt with a mean, which is just the teeth element of this guy, and the t-teeth element of the covariance matrix as well. That's from our properties of Gaussians. Great, and now we're in a position to compute the most probable set of marginal states and the most probable sequence. So let's go ahead and do that for linear Gaussian state space models. Let's do this guy first, xt star. So xt star, that's just formed by doing arg max over xt of this Gaussian here, xt mu t sigma tt. And of course, for Gaussians, the mean is equal to the mode. So the most probable state is equal to the mean. And so because of that property, xt star will just equal mu t. And that means, as a consequence, that x1 to t star, if we collect all of these together, is equal to mu1 to t. Okay, so far so good. We've computed this thing for the linear Gaussian state space model. Now let's figure out the most probable sequence. Let's do this thing. And again, that's really easy. We can go back to the probability for the sequence here, that's this thing, and we can compute the mode. So x1 to t prime is equal to arg max over the entire sequence of a Gaussian with this mean and this covariance. It's just sort of defining the optimization here. And again, because the mean of a Gaussian is its mode, it implies that x prime 1 to t is equal to mu 1 to t. Okay, and so in this case, you can see that it is indeed true that these two things are equal. This thing is equal to this thing. The most probable sequence is equal to the most probable set of marginal states. And so we can say in the affirmative for this guy that this is true. And as a consequence of that, it means that we don't need different algorithms for computing these two quantities. We can use the same algorithm in both cases, which is good news. For discrete hidden state HMMs, it turns out things are different. And it's not generally true that these two things are equal to one another. And so what we'll now do is show that that is true by a counterexample. So I'm going to pick an example where it's not the case that the most probable hidden state, marginally, the set of most marginally probable states is not equal to the most probable sequence. So let's do that. Let me erase this to give us some space. And I'll sort of talk through how I've come to devise this counterexample here and what the thinking behind the counterexample is. Okay, so let's do number 2. So number 2, we're going to do discrete hidden state HMMs. And I'm going to pick an example where life is made easy for us. So I'm just going to pick the minimal version of a sequence model where there are big T equals 2 time steps. Okay, so in this case, the distribution is going to be over variable x1, x2 given y1 and y2. This is the joint distribution over the latent state given the observed state. And again, we're going to assume that, as we have done conventionally with our hidden state HMMs, that x1 and x2 are just scalar discrete variables. And in fact, I'm going to assume here that the parameter k, big K, which sets the number of possible states that your latent variables can take, that's equal to 2. So we're basically looking at binary latent variables, again, just to make life easy for us. And in that case, I'm going to construct a joint distribution, a valid joint distribution over the latent variables x1 and x2 given y1 and y2. So this thing will set up so it marginalizes correctly, but will show that the most probable state, most probable sequence is not equal to the most probable states at each time step. Okay, so here's how we're going to do that. So here's a little table that I'm going to devise, which will enumerate the possible settings of x1, the possible settings of x2, and the probabilities attached to that state. So in the case where we've got binary variables, the set of states can be enumerated. There are 4 possible sequences here, 0, 0 through to 1, 1. And I'm going to assign the following probabilities to these states. I'm going to assign 0 probability to this one, probability 0.3 to this guy, probability 0.4 to this one, and probability 0.3 to this one. So this is just an arbitrary distribution over these variables. And it's a valid density, or it's a valid distribution rather, because these things sum to 1. So if I sum these up, the whole thing normalizes. Okay, so this is something that could be returned to us from an HMM. It's a valid posterior distribution for some data. And now what we're going to do is compute the most probable marginal state and the most probable sequence. The most probable sequence is really easy because it's this thing in here. It's the sequence of variables that gives us the highest, which has the highest probability under our posterior distribution. 0.4 is the highest number in this list. So 1, 0 is the most probable sequence. So x prime 1 to t is equal to 1, 0. It's just this guy in here. But you'll notice something special about the way I've set things up here. The most probable sequence has a 0 here in this element. And just below in probability at probability 0.3, I've got this sequence here, which has a 1 as the second item in that sequence. And this sequence here at the bottom, 1, 1, also has a 1, obviously, and it's second for the second variable here, and it also has quite a high probability, 0.3. And you see that because we've got 2 sequences with quite high probability with a different setting of the variable x2, that the most probable marginal states do not line up with the most probable sequence. So what do I mean by that? Well, let's compute probability of x1 given y1 and y2. So first off, let's consider x1 takes the value 0. So there are 2 sequences which have a value of x1 is equal to 0, and they have combined probability 0.3. So this thing has probability of 0.3 of x1 equal to 0, and of course it must have probability 0.7 of being 1. So the most probable marginal state over the first item in the sequence, well, that's, to use our notation here, x1 star, that's got to be equal to 1. Okay, so nothing's funny so far. It's also true that for our most probable sequence, the first value was 1, 2. Now let's consider the place where the action is, the marginal distribution over x2. So this thing, let's go in and compute it. This is going to get a bit messy, so let's use a different color. I need to look for the cases where x2 is equal to 0. So that's this one and this one in here. And you can see that thing has probability 0 plus 0.4. So this has probability 0.4 that x2 is equal to 0. And then we do the complement of that. The probability that x2 is equal to 1 is 0.3 plus 0.3. Yes, so this all checks out. This is 0.6. x2 is equal to 1. So x2 star is therefore equal to 1. And collecting those two things together into x1 to t star, this thing is equal to 1, 1. And you can now see that these two things are definitely not equal to one another for the reasons that I sort of laid out intuitively earlier. So for discrete hidden state HMMs, there's this important property that you should know, that the sequence of most probable marginal states is not equal to the most probable sequence. So if you want to compute these two things for a discrete hidden state HMM, you need two different algorithms for doing it. Okay, so big picture here is there are lots of possible inferences that we might want to make. There are distributional inferences, and they might be wanted to be computed in the online filtering setting or the offline batch or smoothing setting. There are also point estimates, and you might be interested in the most marginal, you might be interested in the most probable state marginally, or you might be interested in the most probable sequence is. For linear Gaussian state space models, those things are the same, but for discrete hidden states, they're different. And so there are different names and different algorithms attached to all of these different quantities. We're going to keep things simple in this course, and we're just going to look at the marginal distributions in the context of filtering. So we'll talk a little bit about that over the next few video chunks. We'll look at it for both linear Gaussian state space models and discrete hidden state HMMs. The reason why we're focusing on this, as opposed to any other sort of item on this slide, is that this filtering problem is sort of often used as a subcomponent for solving more general problems like smoothing and joint smoothing. So you'll see these filtering algorithms showing up in the solution to these more general questions as well. Then once we've covered inference, we're then going to talk a little bit about learning before we wrap up this section of the course.